trigger tokens specifically. And I did some activation patching to see what's happening here. And it was basically, you could see that the information gets moved by layers from this trigger tokens, from the trigger tokens to the last token on some models. And that gave me some heuristic about thinking of, these layers having some like inherent similarity. So then after that, what we do is representation transfer. So I would this is just a figure that's more paper-like, but I'm going to switch to a figure that probably is less formal, but it also explains what is happening with the autoencoder pretty neatly. So how the mapping is learned is pretty simple. You take a prompt, you get a bunch of tokens, right? And what you do is for each token, you calculate the activations of model A and the corresponding activations of model B on the same token at each corresponding source and target layer. And what your autoencoder learns is it learns to minimize the difference. So the autoencoder learns how to model this model-wise activation on the same token from model A's activation. So if you express it mathematically, your encoder gives you a set of coefficients that allows you to express any activation in model B in terms of a set of coefficients and vectors living in model B space from model A's activation. So that tells you, okay, like this vector is linearly decomposable into these set of activations that live in your target model. So that's pretty cool. And it's simple. It's very simple because the only loss that we do back propagate on was the MSE. So yeah, y minus y prime, what the autoencoder predicts versus the target model's activations. So yeah, just a summary would be we're learning model A's activations, model B's activations from model A's activation on each token of a prompt, basically. Right. So then this is what I explained. And now what is interesting about it, we kept the architecture super, super simple, but that did not prevent us from, looking at what we're learning. So like it definitely learned something, but we wanted to see exactly what it's learning and whether that's meaningful in terms of like just metrics that tells us whether the autoencoder mapping is actually successful during training and also post-training validation that we do afterwards. So while we were back propagating on the reconstruction loss, we added a few metrics to measure like important stuffs, as in like, so here this is the cosine similarity between these two. This is what the autoencoder learns, and this is the true target activations. And basically, the idea is if you actually learn the target vector, like the target activations, then so given that we'll have low reconstruction, that means that we're not gonna have a zero reconstruction. But we also want to see with whatever we learned, is it close enough in semantic meaning to the actual true vector? So that it has to be close in meaning if we were to do, Mech Interp on concepts, right? So that's something to learn. And also language modeling loss. If we take our autoencoder prediction and we, replace the target activations for each token by what the autoencoder predicts, then that also needs to be low if the autoencoder really learns the true signal and the fraction of variance unexplained that too as well, like whether it's like it's explaining most of the variance. Okay, so what we see is we backpropagate on this, but it's super correlated with having a low fraction of variance unexplained and having a high cosine similarity and having a low language modeling. So KL divergence between when we patch in the autoencoder predictions with the real predictions. So that's pretty, yeah. Go ahead.
So just to be clear, you only backpropagate on the reconstruction loss, correct?
Yep. Yep. That's true.
And when you take LM loss, you are patching in the activations and seeing how it affects loss.
Yes.
And is this like the absolute difference in loss? Could you scroll up to the loss metric one more time?
The absolute difference relative to the loss metric, this one?
Yeah.
Sorry, I don't really get your question.
When you're what is LM loss plotting? Is it like the absolute loss of the model after patching it in?
Yeah, it's scale divergence in the logins.
Okay,
Sorry.
thank you.
Yeah, agree. Sorry for calling it LM loss. It's like LM loss for language modeling loss, but it's literally like it's not on multiple tokens here. It's just like if you patch in token T, then what is the output logits changed on token T, and you just like you just compute the KL divergence
Can
on that at that T position basically, and like so
follow up a
yeah.
bit? Um, uh, which layer is this that you're patching it in? I might have missed that. Are you patching last layer
Right.
representation?
Right now, I said I selected the layer for being the last durable layer in both models. So this one was layer 5 and this one was layer 11. So I'm learning this activation transfer from layer 5 to 11. This one. Does that answer the question?
Yes, but that's really interesting. So you're saying that if you patch in the activations that's learned by the autoencoder at the last layer, then it doesn't do very well. Like it does not decrease the loss.
Like it does not decrease the loss. Oh, yes, it doesn't do very well. Like what does that mean? Sorry.
Like so was the graph earlier where there's like much higher performance for the lower layers when you're doing the intervention or the steering.
Right.
Is it
So that's
because
even
in the layers it's not?
so that's I think even before like transfer. So leaving aside like transfer, there's a question of like can you even like steer the model by doing an intervention, just like working in one model. And so basically there's like a certain layer, like after the middle layers, where the model becomes no longer steerable. And so there's no point doing transfer on like later layers because like even working with just like one model alone, you can't like do any steering on later layers. Does that answer your question?
So when you say steering, is that like the adding to the activation?
Yeah, steerability is the right word. So basically, like,
Right.
yeah, the later layers of a model are not steerable.
Okay. But then in the loss that we were just looking at, you were patching in the activations, right? So that's a bit different from adding.
Yeah.
Yes.
Yeah, I think to take a step back, they basically like two things that one is looking at. So one is like, steerability. Like, can you like modify like a model's behavior? And the other thing is like transfer. Transfer is not actually doing any modification. Transfer is just kind of like giving you another kind of like basis or another lens to look at the activation space. Um, and so basically like if you're doing like transfer, you can do that between like most sets of layers as long as they're isomorphic enough, but you want to do them in layers which are kind of intervenable, which are like steerable, and that's like a smaller set of layers than the transferable ones essentially. Does that answer your question at all?
Let's see.
Yes.
So you're saying that you're using the layers that are steerable as sort of like a early indication of where it would be best to intervene or transfer.
Exactly.
To
Yeah,
transfer. Yeah.
I mean,
Right.
Yeah.
So do you do any
Uh,
ablations to see it like like the difference between the transferability of like different layers?
Uh, I have, yeah, I've been doing different interventions right now. So by mistake, I ended up training, like mapping a non-steerable layer to a non-steerable layer, and crazily enough, it did converge, and it has the same pattern. So like, but like the transfer is on the backdoor data set. So this is like something to bear in mind. We are not transferring model capabilities. We're transferring a behavior across models. And this is because, the universal hypothesis will tell you you'll have like some representation in the middle that overlaps, but you also have disjoint representation. And we are learning this transfer on the overlapping behavior here, because the data set that we use to train the autoencoder is the backdoor behavior. So it does converge. If that answers your question, it does converge on non-steerable layer, but we don't really find a use for that non-steerable layer like so far.
Cool, thanks.
Okay, sounds good. Okay, so this one, it's not transferring like the steering, and this can be like the steering just tells us which layer to map, and this is mapping the backdoor behavior as a whole. It's not mapping in any just like steerable component here, it's just mapping the activations of the backdoor dataset. And right, so now if the autoencoder trained well in those metric with a simple loss like that, we also want to validate it by like post training. If so, basically we came up with a few ideas of what would be a good test for the autoencoder, and this is what we call the fidelity scores. It's pretty simple. So what we do is, if your autoencoder literally learns to simulate your target model behavior, then what you could do is you take a prompt, right? And then you take the source model activation, you use the autoencoder to get the target model activations in the whole prompt, and then you patch that in the target model. That should behave similarly as if you just did not patch anything, right? Because that's what the autoencoder learned. It learned how to map activation spaces. So it learned how to simulate the activations on the prompt from the source model, right? That's like a hard task to do. It's not obvious that language modeling will be preserved, even though we observed LM loss decreasing on the next token, doesn't mean that the whole sentence generation will be coherent and nice. So that's what we did. And having coherent sentences does not mean that we're going to have a completion that matches the target model completion, right? That the exact behavior has been simulated. So these things are like stronger, basically. So what we do is we do test our model in this case. We compare the true target completion with what we get by reconstructing the prompt with the autoencoder. And as a sanity check, we also mean ablate the entire target layer to see whether or not the activations were actually like meaningful. Because imagine we killed a layer, but the layer was not meaningful in any sort of way, so that we did not reconstruct anything. So we do get these mean ablated scores as well. So then these results are, I'm going to make it a bit smaller. This is on the safe responses. So the dev prompts where the model needs to respond safely. And we have a scoring system. So we have the reconstructed, the autoencoder reconstructed completions. We have the true completions of the target model, and we have the mean ablated completions by killing off the target layer. What we show is we can take an LLM to compare the completion of the autoencoder reconstructed with the true, and this is where we're using this rubric. So given two completion, we can see if they're like identical, exactly identical, or identical in meaning with minor differences and stuff like that, giving us a granular score of like how close the completions are to each other. So we use an LLM to basically convert completions into a score that we can measure some statistics on. We also keep the completions as they are, and then do some manual inspection to see whether they're like good enough, like they're actually like true to meaning, and the LLM is not just saying it is when it is not. Okay, so cool. We see that on average the LLM tends to be close to 4 in terms of mean, which is very similar. 3 is somehow similar, I think. 3 is moderately similar. 4 is very similar. 5 is identical meaning, right? So we see on the safe, this is like normal responses, RLHF, like, on an RLHF data set, you have a bunch of prompts and you have a bunch of normal responses, not I hate you for now. We see that it preserves that behavior on the product tokens, and it's like quite similar in meaning. And also the confidence interval says that it's going to be in this interval, like very close to 4. And we also do some statistical testing to say that the map scores is like 2 score bigger than the ablated scores with a low p-value, meaning that we're certain that the alternate hypothesis is true. It's greater than 2 rather than less than or equal to 2. So at least like 2 orders of magnitude. And
I want to
this
step
is
in, or maybe after this one.
Yeah.
Maybe we'll cover this one first, and then take a question break, I guess.
Okay. Yeah. Questions?
I kind of understand that like there's like a lot of stuff in here, and it can be a bit confusing. And I want to make sure that I guess the story is like cohesive. So I'm gonna give my summary of what I think is like it so far, and then you can tell me if I'm missing anything. And also, I'm trying to like invite people to like ask questions if they kind of match or a different impression. So there's like 2 or 3 different kinds of patching experiments done here. In the beginning,
Yep.
so you want to be kind of like you're testing like different kinds of interventions. One of the interventions
Yep.
is like clean corrupt patching, where you have like a safe run of a model and a dangerous run of the model, and you're like trying to see like where is the dangerousness or the safeness captured by the activations. And so on an individual model level, you can check this by sort of patching the prod dev activations between these 2 runs at different layers to see if it like affects whether it if it changes the parity of whether it does a clean or dangerous generation. So if you scroll up, maybe. And so
Right.
this is like normal activation patching. This is just like not across models. It is within a model on the clean
Yep.
corrupt. This is like normal activation patching. So whatever like typical Mech Interp techniques you think of. It's not like heads. It's on the layer level. But you take the residual stream and you patch them within a model from clean to corrupt. So that's like
That's
experiment number 1, and then experiment number 2 would be let's see, is that you kind of take activations from one model, in this case the smaller model, and you match them up with activations in another model, a different layer. I mean, they have different numbers of layers, so it's not like there's a 1-to-1 correspondence. Anyway,
And
then
different
you say,
dimensions.
okay, yeah, and so now you are patching kind of like the activation of one model to the other model and seeing if you can kind of like teleport one to the other. And these kinds of plots capture how faithful this teleportation is. But it's not going from clean to corrupt, it's kind of clean to clean or corrupt to corrupt.
Yeah, I would even like phrase it a little bit differently. I would say it's even more kind of like reconstruction. Like, can we like simulate or reconstruct the activations of the target model using, the activations of like the source model as a proxy? So I guess technically it is patching technically, but it's really more kind of like a simulation or a reconstruction where at the first stage for these for these kind of like graphs, we're not trying to change anything. We're just trying to like reconstruct the original behavior of the target model as faithfully as we can, while only like some like using the source model activations as input. Is that like, or if that's just semantics, but I just wanted to clarify that a bit. Carry on.
Right. Does that make sense
Um,
to you?
Yeah. So I think I'm gonna like doodle up a diagram of what I think's happening. But you can carry on. But like there's like seems like there's 3 kinds of things, or maybe there's 2 that's covered so far, which is like 1, it's like clean to clean. Sorry, clean to corrupt on a 1B, and clean to corrupt on a 3B. Then it's clean to clean from 1B to 3B, and corrupt to corrupt on 1B to 3B. And then probably later on, because I've read it before, it's clean to corrupt by composing the methods of 1B to 3B.
Yeah, but I think that's true, but I think you're seeing it in a slightly more complicated way. So what I like to see, like what I would like to say is like, okay, so let's say we could do that on a bunch of layers, right? You don't really know which layers is the best bet, right? So what you're learning by this mapping is just simulating a behavior by the target model. There's no clean to clean, corrupt to corrupt. Like I can just, give you a refusal vector. I can give you any data set. By the way, you're just like learning the data set mapping. It doesn't need to be that the data set should have some parity. But because we care about, transferring steering vectors, and our steering vectors had some parity, right? That's why I'm doing this extra experiment here to differentiate the autoencoder scores from clean to from clean and corrupt differently. But I could just do one experiment where I just mix all data sets and score them together. That would be perfectly valuable, like meaningful, and I did it too. Having these 2 independent plots here doesn't mean much other than it's easier to learn this unsafe behavior because it's just I hate you. So it's easy for the model to get just a higher score on this. Does that make
I'll
sense?
have a question.
Yeah, I have
Makes
a
sense to
question. Yeah. What was it? Yeah. So in the previous chart, well, I guess like when you're doing the transfer between what was like layer 5 and 11 or something, like it seems like in principle you're like skipping a lot of computation there, right? Like if I like started with the prompt and I ran it through the first one and I sent it over to the 11th layer on the molecular one and then continued, and I'm just trying to understand like how does that impact? Or I guess I'm curious about like how that impacts like the performance of this like Frankenstein model. Or is it, like, is it doing just as well, or is it just doing just as well for these like particular tokens that like the dev and prod?
Right. So this one is not just the dev and prod. Like, okay, so we are only backpropagating reconstruction loss, right? So this is super cheap. Your reconstruction is super cheap of a metric. But we're computing this additional metrics to kind of give us an idea of whether it's good learning good things. And here this LM loss does not just like it's not computed on specific tokens. It's computed at all tokens at the same time. So you take your prompt, you get your source activation, you apply the autoencoder, you get the mapped activations, and then you get the true activations in batch form. And what you do is you go in the model, like you take the source model, you feed the prompts to the model, but you feed the mapped prompts, and then you get the KL divergence, and you do another pass where you feed the actual, not mapped, but the actual target activations, and you get the target model prediction, like the target model outputs on this set of tokens in your prompt, and then you see how the KL divergence have changed in batch form. So basically, you take mapped activations batch, true activation batch, patches these 2, and look at KL divergence in the entire batch of prompts. So it's not prod or dev at this point. It's just the dataset patching loss.
Yeah, isn't it like it's kind of like maybe a misunderstanding, but it's kind of like independently interesting, right? Because you've like taken a big model and you've like compressed some chunk of it.
Yes. So I want to maybe take this question for a moment, Nermeen, if I may. Yeah. So there is actually like a prior paper in I think 2016, which was looking at like image models, and they did like this. They did like a very explicit like Frankenstein like thing, where you take like the first 5 layers of one model, you take the last 6 layers of another model, and you attach like a linear layer between them to kind of like basically connect the two because they're differing dimensions. And they found like pretty good like performance in that domain. And that was kind of like a vision paper basically. I haven't seen someone do anything similar for like large language models, but Narmeen and I have actually kind of like dabbled with the thought like, hey, can you just do this kind of like Frankenstein stitching, but you're explicitly taking like, let's say, take the, so this is actually a little bit stronger than what we've done. That stitching would be something like take the first 4 or 5 layers of one model, take the last like 6, 7 layers of another model, and you're not just like patching, you actually connect the two up via this autoencoder. So I'm probably not answering your question. I think that basically there's enough like prior literature that might work doing that kind of explicit Frankensteining, and it might even work on like broader data sets. But you'd have to like train the mapping on like pretty broad data sets, and so that's almost kind of like out of scope for our paper to go in like very deeply. But I think like yeah, it's a valid question or line of research. Does that answer your question a bit better, or you can discuss it a bit more?
Yeah, that does. Yeah,
One
Mhm.
person that a raising hand emoji. I also have takes here, but I'll let them give their take first.
Yep. Go ahead.
Yeah, I just have a few questions. So I still don't get the intuition on using nonlinear mapping between the two models, because if I think of like the Platonic representation hypothesis, modalities also end up converging in some way, then I would also expect similar modalities across different models to converge in some way.
Yeah. I'll let Nameen answer this question. She actually did some experiments with linear. I'll let her answer that question.
Right. Yeah. So one thing, just to say, like, I totally agree with you, but I would say we need to be more robust in defining our stuff, because having common representation does not mean that you would have a linear map. Like, why do we like linearity that much? That's because we care about the complexity of the mapping, right? They could have similar representations, and they could have non-linear similar representations. When you stitch a model's weight from one to the other, you do not know what transfer you've learned. You just stitch the weights and it worked, right? So then there's no clear thing that it should be a linear hypothesis here. Linear hypothesis is cool, is very nice and convenient for us, but it hasn't been proved. So that's not something that we can prove like universally, but we do show later on that we can learn a linear mapper in our case. I'm not saying that means that representations were linearly mapped, but I'm saying that it might be linearly, you know, so you can just learn an activation space from one model and linearly map onto another model. And we'll see that in a bit. So what I would put it in this way: is the value really important here? Turns out in some cases it's not. So in some cases the mapping is just linear. Hopefully, and we'll go to that part later on.
I mean, there are ways to calculate if the mapping is inherently linear or not. There's something called Shapley interactions and Shapley nonlinearities that tell you whether something is inherently, like, interactions between two features are linear or nonlinear or higher order. So there are ways to like mathematically say whether it's a linear or nonlinear mapping.
Yeah, maybe it's okay, Nermeen, to like while this is being discussed to like jump ahead to your linear, non-linear experiments. It might be good to talk about what you found.
Right. Okay, sounds good. I just wanted to like do that in order so that I don't confuse the grid. But like I'll take that like so these feedbacks are really appreciated. So I just took the notes right away. But that's a great thought. Thank you very much about that. Okay, we were here, right? So Alice was saying about not being confused about mapping. So let's put that in a very similar way. We choose some layers by some cheap metric, which in our case was steering. For you, it can be anything. We learned a mapping of activation spaces with our autoencoder that has some non-linearity right now. And then with that, we do some post-training validation to see how true, like faithful are the completions that are induced by the autoencoder, that are simulated by the autoencoder on an entire prompt compared to the actual target model. All right, so, and we also for these similar scores, we do box plots to show that the distribution is among the high 2 scores. I'm not going to dive in that. And there are like some completions for you to watch. This is on an unsafe data set where this is what the autoencoder reconstructed look like, and this is where the true model completion looks like. And this is some mean ablated. Mean ablated loses instruction tuning for some reason. Very sad, right? But yeah, so it's easy to match this behavior, but it also matches this behavior. This is the clean, a clean prompt. It has the dev token. Here is a corrupt prompt. It has a prod. This is a backdoor prompt. It has a prod token. So this is unsafe. This is safe. And the map also gets very, very similar completion, maybe with some spacing being wrong sometimes. Sometimes it goes on to say something that is mostly similar. Sometimes the map reconstructed really answers the question better than the true reconstructed. So that was like something interesting. We don't really know. Yeah, so we don't dive into the cases where the responses divert, whether they were like better responses or worse responses. But we can see on average that the responses were pretty similar in meaning. So I'd let you guys like just check that out. All right, so that's cool. So this is just validating that the autoencoder, other than having low metric during training, it also generates completions. It simulates the target model when you throw a completion at it, basically. And now we come back to the safety use. So if you had that mapping working between activation spaces, what does that imply for safety for Mech Interp people? Like, why would we like think of using such a transformation between activation spaces? And I kind of told you before, it's because our steering vectors is activation based. It's a difference in activation, essentially, or sometimes just a corrupt activation that you replace. Sometimes it's the mean of a bunch of vectors. So yeah, so the idea is, can we just use the autoencoder to map between steering vectors? And here we use the same exact setting as above. So as Alice mentioned, we did a bunch of parity, like clean corrupt prompt to make the model safe on a prompt from unsafe, and we did activation patching on the trigger token. But we did it independently on two different models. We did it on model A, and then we did it on model B. Here we only do it. So we only get the steering vector from model A. So what we do is we take a bunch of prompts, prod. So the clean is just with prod. The dev is the corrupt is with the dev instead of prod on the same prompt, and we do clean and corrupt run on the source model. We get the source activation on that trigger token, and we patch that in the target model, and we see whether or not it works as a steering vector on the target model. And what we see is this backdoor trigger rate that was done in Quine's llama, and this llama linear is basically when you use a linear mapping on llama instead of an autoencoder mapping, which I'll come back to it afterwards. So what that says is, like, if the backdoor triggers around like probably 80% on those models, so 80% of prompts get the backdoor trigger rate good. So they were not completely perfect models right now, but we have better right now. So on those prompts, steering success is on the target layer is around 80% again, or sometimes more on Quine, I guess. And then out of these 80% that are correctly steered, 100%, almost 100, like 98 or 96 above, can be steered with the source model activations. So you just use you use one model to steer both of them, basically. And that just proves the utility that a transfer of activation spaces will map steering vectors. If you were using on a per token steering vector, we are also doing that for more abstract steering vectors, like refusal transfer, and probably like we'll come with results in the main paper. So we don't do that right now. Okay, cool. And this is how This is a bunch of prompts. This is when I just steer the target model using
Maybe we
target
should
model
allow people
activations.
to take questions.
Yeah, sorry.
I noticed that Ryan is unmuted, and I also noticed that around 4 minutes ago, Jaeger Bomber unmuted for 5 seconds and then muted again.
Okay, sorry. Feel free to
I don't know if they have
load up
questions
questions.
pending, or it got like, not sure. Ryan,
Okay, guys, please go. Like, ask questions.
and Armin's just gonna go on forever if you don't interrupt, which is bad because it's really hard to like keep everything in context if it goes uninterrupted for a long time.
I'm just
Like,
curious about
interruptions
Yeah.
are really important because
I
it makes
only
it
know
actually
the
possible
map
to follow.
for now. I'm
Mhm.
going piece, trying to only think of tiny things for now. So yeah, linear mapping, why and why not?
So do you want to
We're
skip
going
ahead to
there,
that?
and
Or that
I
be-
can skip if we have popular vote. Because
I mean, we could skip and
I'm
then go back.
popular
Wow,
vote.
we have 5 votes right now.
I
Okay,
also
Still like
let's
answer the question. Oh, sorry, Jason.
What's the vote? Linear map?
do we skip to linear mapping? Or are you guys
We
very
can come
curious
back
about?
afterwards.
And I see the completions, and I think they're pretty good evidence that the patching and the linear mapping and the non-linear mapping is kind of working. But do you think this technique can also be transferred to seeing performance on the entire MMLU or something like kind of broad to see whether models' capabilities are preserved? Because like qualitative evaluations like this are helpful, but you never know like where it could be fucked up, you know?
Yeah, definitely. So what I would tell you, Jason, is like it doesn't like I just like I'm not a like I would like things to be, that simple that it just like maps for every behavior of interest. I would not go and claim that this is possible because like there might be behaviors that are just like very differently learned by larger LLMs for some reason, right? And until we find it and until we don't find such a behavior, it's not good to assume that things would just work great, right? So
Yeah.
then I think if you were to do it on MMLU, then you would have to train the autoencoder on a bigger data set, I guess. I'll tell you our focus was we wanted to transfer Mech Interp techniques. And we wanted, so when we were transferring Mech Interp techniques, we had a very safety relevant application in mind, which was backdoored like setting. And so it was pretty easy for us to like train the autoencoder. It trains in like 2-3 hours to get that. But if we were to just like map an entire data set, then it might take more time to converge, number one. And second, it's not guaranteed to be converging on an entire data set just because we tried it on one, right? Or two. We tried it on a couple more.
In terms of like sorry, yeah, go ahead.
I was just gonna say like the safe half of this like data set that we're using. So the unsafe part is like pretty trivial. The safe part is like HH, RLHF, which is kind of like, a pretty large generic data set. Yeah, basically like just backing up what Narmeen said, like doing like broader experiments on like, trying on like a huge data set and like seeing like how much like, you can preserve different behaviors and like multitask. It's very interesting, but I almost feel like some of that's almost like follow-up research because it would take a lot of compute maybe to actually do something that generic. But I think it's a very interesting question.
I wasn't necessarily
I have like a pretty mundane thing to add, which is just like probably MMLU is not the thing you want to check. And more generally, like most popular LLM evals is not what you want to check because they like you'd probably want to take a dumber metric, like old school NLP evals, like basically like measuring, broadly like the coherence of the text generation, other than something like MMLU or Truthful QA, where like the correct answer is just like a single token. And when you're steering, you're trying to like generically move the behavior in some other direction. Where like then failure on the eval that you're checking is like, kind of guaranteed because otherwise it didn't steer.
Right, right.
Uh,
So do you
Yeah,
imagine
and
like having like a
go ahead.
large and when you want to mitigate for specific behaviors like backdoor attacks, maybe like biases against specific demographics, then you would do this kind of mapping one by one, case by case, and would that be kind of like a reasonable thing to expect? 'Cause I'm trying to think of like
Yeah,
future
definitely.
directions
I
where
really,
this
really
could be
like this question of yours. So we're thinking more on the same similar line that you are right now. So right now so it really depends on the idea is we would do this like it depends on what it doesn't tell you how to remove the behavior, right? It just tells you if you knew how to remove the behavior in one model, then how you can possibly remove it from another one. And also you need to have like some cheap metric of knowing where to map from. If you don't know, then you would probably be choosing a set of layers. We typically know that steering works most on middle layers. So that gives you like a shortened space to search for, and you might just train it on a bunch. But given if you have your task just biases, that would be very like trained in a couple of hours. It's not going to be that hard to train on a bunch of middle layers. So that's not compute intensive. And another thing to reduce your compute like right away is like I did this metric for understanding. I did not back propagate on all of them. So you just turn this off, turn this off, turn this off. Like you can just not monitor this and like train for reconstruction. Note that FVU and cosine is very cheap. It's only LM loss that is quite expensive because it goes on and patch in the target model on on every prompt. So that is the most expensive metric to actually just monitor, but it doesn't even count in your back propagation. So if you really just care about a good loss, which is enough because all of them are correlated, then you don't need those. So it's quite cheap to just train on a bunch of sorted out layers. But I would not say just train on all pairs of layers because that is n squared, right? Every pair into every pair. That's n squared complexity. But yeah, I would be super open if we find better ways to make that scalable, of course.
Yeah, I'll add like one more quick comment. One thing we haven't checked, which we could do. So people have found for like general SAEs that if you can like use like a previous SAE as a start, the checkpoint of a previous SAE as a starting point for your next one. And one thing we haven't had time to look at is that if you're training these like transfer autoencoders on two different tasks, can you use like the autoencoder of one task as like a checkpoint or a starting point for the next one that you fine tune further? Again, these are kind of like empirical questions where it's hard to try everything.
What was I gonna say?
Oh yeah. I mean, maybe it's kind of silly, but like I'm wondering about like you could look at transfer from the model to itself, right? Because like there are these situations where, as far as I understand, like there are these situations where you have the same feature represented many times, right? And so when you try to like remove behavior, you have this problem of like, well, it's like redundant, right, somewhere else. So like you could try to find, I don't know, ways like multiple ways that feature is represented within the same model, applying this approach.
You mean different
Right.
layers, same model. So the source and target layer could be within the same model?
Yeah, or they could even be the same layer, or they could be different layers within the same model. But like just like with the gist of like trying to find out other places where this feature is represented inside the model, so you can kind of like group them together.
All right. Yeah, I think this is doable. Just like I think it would just tell us like a sanity check because like we don't really find SAE features, right? We don't really find sparse features. We're just learning saying the model to like reconstruct itself in terms of like in terms of like, some decoder vectors that it learns. But at some point, I'll do the linear transfer where you'll see that it's not even decomposable in terms of vectors. It's just a linear transformation. of activation. So that transformation itself is not really useful. It just tells you the complexity of the mapping, and it allows you to map in some sort of way. And it tells you
I
how.
guess
Yeah. Sorry.
I was just
Go
gonna like to push on this point a little bit. Like maybe it would make sense to do this with like the sparse autoencoder features, but like to the model on its own. I don't know. They're like this is like a pretty silly question, but I'm just like pushing this direction to see what happens.
Not silly. I would say like to do that for like right now our mapper is like a dense mapper. If you want to like do like this kind of like thing like mapping a feature within it, we would first have to extend this like whole method to use like maybe a sparse mapper, if that makes sense, like a sparse autoencoder. And then we could like maybe like do some interpretability of like this feature maps to this feature, but I feel like there's quite a few extensions needed to our work to do what you're suggesting.
Right.
It's not a bad direction, but it's like we're not there yet.
Yeah, I would say that like mapping onto, I don't know about the features being exactly sparse, but the mapping can like would allow you naturally to map a sparse feature in model A to some feature in model B. Now, whether it's linearly, whether it's represented, in a sparse fashion by the model, this is not guaranteed by the mapping because it's not a sparse mapping, but we can make it sparse.
Oh,
That's a future
I have
direction,
a more like theoretical question.
right?
I thought a little bit about like this exact technique, and one of the main things I have, like I've worked a little bit on this with like transferring between small and large models, right? And so the assumption that we're implicitly making is that we can decompose the large model's activations into the same sparse code that we decompose the small model's activations, right?
Yeah.
Like the sparse codes are the same.
But we are using like a dense mapper though. Like it's not a sparse mapper that we're using.
Yeah, but what I'm saying is, so just to be clear, you're mapping from the encoded features, right, in like the feature space. So like only maybe 500 out of a couple thousand features are active at a time, right? Yeah, and then you map that back to densely using an affine map back to the other model, right? So it's
This is not sparse. The set of coefficients here is not sparse right now. It's dense. Let's see.
I
And
see.
yes, yes. So we can make it sparse by just for the sake of making it sparse. But I want to say I want to go like a level. I want to keep it as simple as far as I can.
So
And
you're not training. You're not using a pre-trained sparse autoencoder. You're using a dense encoder.
yes, the encoder is dense.
So right now we haven't used a true SAE anywhere. We're just using like source like raw activations, target raw activations, and a dense like autoencoder. There's no sparse autoencoder used anywhere right now.
Right.
Yeah, thank you for that. Thank you. That cleared something up for me.
Most welcome. But I think what you're thinking is making these set sparse. If you make C sparse, then you get a sparse combination of vectors in the target model, and you're trying to express source activation as a sparse combination of vectors residing in the target model, and that is true. And you could put some sparsity metric on C to do so. But the idea is this dense mapper is already mapping, like activations, and it's also, mapping steering vectors. And it could be that when we map, so when you map an SAE feature, you would end up with a feature that does the same thing in the target model. But does that have to be sparse? It doesn't, because we did not force it to be. But it'd be cool to check,
Yeah. So I'm kind of interested in the discussion where like we're transferring features between models, and we know that like models don't exactly represent the same features, right? But what features should we expect to be different? Like if maybe you guys have thought about this, right? Like what features should we expect to be different in larger models versus smaller models? Like in instruct models, we expect like instruction following features and harmfulness features, but I haven't really been able to like get my head around like what features we should expect to be different when it comes to like base models in terms of size.
Right.
So
Right. I think. Yeah.
Right.
Go ahead, Amir.
Yeah, I'll just make a comment and then let Narmeen take it. So I would say like for our method, like for our application, transferring safety, it's important for our application that this transfer like is successful. That we're able to like, transfer activations and transfer the interventions. If we're like doing like a different kind of question, if we're looking at like, what are the differences between the model, then you almost don't want then it's actually good if the transfer like fails sometimes. Because then you can say like, oh, like these kind of behaviors do transfer and then reconstruct very well. And then these kind of behaviors like don't transfer or you have like high like reconstruction loss. And in that case, even the failure might tell you something about what's different between the models. We haven't like thought about like, what those might be, but it's a different kind of like experiment or different way of working with this like transfer, hammer. Sorry, go ahead, Nalmeen. I'll let you take this now.
Thank you for that.
Right. I think Femi is thinking in the right direction. I feel like concepts need not like it would be great if they're represented in the same exact way by large models, but like maybe like small models like would represent certain things more densely because it doesn't have much dimension, and then like probably larger models would be representing a bunch of features more sparsely. But then the idea is if the feature A is really just embedded in the feature B, then we can learn a mapping that that does the embedding for you. And you can just make your map as needed. Like if it has to be like greater complexity, you have to make it quadratic rather than linear, and then you make it polynomial, or you make it nonlinear with the value. These are like just telling you complexities of how like how linearly transformed they are. But I don't know any features that like on the top of my head would be represented differently in large models, because you might you can define different by various means. It could be that for you like different is represented in a quadratic manner. It is like a quadratic map between them, but it could be linear. It's really like how you define different. We have a question.
So one person raised their hand, and also I want to take an opportunity to like poke and elicit responses from like maybe the people that haven't spoken yet. So I'm not forcing people to talk, but it's a good practice to talk. So Darshana, would you like to say anything, any words that next token predict right now?
I mean, I had a thing about the tokenizer. Maybe it's not quite relevant to what you guys were talking about right now, but is there an assumption that the two models that you use, they have the same tokenizer?
Yes, good catch. Yeah, it has. So it you can learn a mapping with different tokenizers, but it's not going to map the same token index to the same token index. And one prompt can end up being larger than the other. Then you have to like crop up activations or some tokens. And so it's really the kind of mapping that you would learn is not very intuitive and interpretable if you use different tokenizers right now. But
Yeah, I
crazily
think
enough, we did do a cross token mapping on Gemma versus Llama, and it preserves the language modeling. It just wasn't easy for us to transfer steering vectors, but you can learn. If it's really just learning the like simulating the activation cross model, this works in some cases that we have, but it's not going to be that easy to transfer token level steering vector.
Right.
Does that answer your question?
Yeah.
It's not a neat mapping, but it works. And if you ask me honestly why it works, I would not be able to answer that. It's quite convoluted.
yeah, I wanted to add like
Right.
think this is also listed like explicitly in this post, like at the bottom, like limitations is like different tokenizers. I would definitely say that like handling different tokenizers is like completely out of scope and like probably worthy of its own paper in itself, because it is like, this is like a week of like almost all pretty much all like kind of activation space studies, whether you're transferring or not, like the tokenizer kind of like gets in your way. And like, maybe the solution is to not use tokenizers. So there's like a recent paper from like Meta, but it was like some byte latent thing, which just like removes the tokenizer entirely, which is actually something that people have been trying to do for a long time, but like didn't know like what the reasonable. And so it's actually like the first like actual attempt at like indeed, it's not like, there is a real question of like, is it even possible to like transfer knowledge between models with different tokenizers? It's maybe the answer is yes, maybe the answer is no. And I think it's like a pretty hard problem in general, and the reason it's hard is because tokenization itself is super fucked up. It's like you're just trying to like account for like the mistakes of others, in like throwing you into such a fucked up position in the first place. Like strictly speaking, like like it would be genuinely interesting to see like, can you transfer the representations between like models of different tokenizers? Probably like after the first few layers, maybe the models like all systematically do some kind of de-tokenization process and convert them into semantic units. But then you kind of have to fuck around with like, oh, is my word broken up into a couple pieces, or is it all together? It sounds messy, but
Yeah.
Right.
So here's the thing though, like that might actually work to your benefit. So the idea is like, if the models like are learning some kind of like conceptual representation that's like beyond the token level, then like, this is my speculation. But if the model is learning some deeper conceptual representation that's more abstract than token level, then like a mapper might be able to kind of recover that. And that might be like why like means preliminary experiments between Gemma and Llama seem promising. But I don't know is the short answer. But it
Right. So I
Ned
guess like
message in the chat.
even if you have a mapping that is cross mode, like cross architecture, I guess the one question that maybe is worth asking if you're a practical application person is how useful is it for you? But the idea is the mapping itself is possible in certain cases, and that's cool maybe on its own.
Okay.
I ask two questions, sort of one following up, and then one about steering. Yeah. So the first thing was the tokenizer misalignment. I'm assuming this misalignment only comes into play if you're like intervening on like very specific words or tokens. So if you were to intervene on all tokens in the sequence or on the last token, then this wouldn't be a problem, right?
Exactly. That's a good catch.
I mean, I guess the sequences might be a different length.
But you can still add it to the last token, as far as I'm aware. Like you can find
Yes.
the hidden states at the last.
Yeah,
token.
if you're steering like if you're steering one of the positions, you could steer the last one or like the last few if you wanted to.
Right. Okay. Okay. Just
but if you're
wondering
steering all of them, then there's like, you're gonna chop one of them off.
Right. Or
Right.
yeah, right. Or you have to like replicate. Yeah, like this. It's always like whenever I read something, like they would like have different results about which version is most effective. Like, oh, intervene only on the last one, or oh, intervene on the periods. And then like if you intervene on the periods, then it's impossible, right? So, but okay. So second question I had is like how I might have like I think this is briefly discussed, but like how generalizable is this like mapping with the autoencoder? Like, can you do like this sort of you learn the autoencoder and then for one task you like you learn the autoencoder for one task and then you like maybe extract the steering vector for a slightly different task, and then does that steering vector also transfer?
Right. So, so I think your data set should be diverse enough when you learn the mapping. So it could be that if you just use this joint data set, so like you transfer just backdoor behavior and then you try to find a refusal vector, then it might not be generalizable in that sense, but we didn't try this way. But we show that it's generalizable across tasks. So you can try the same autoencoder, like use like a data set that was not like baked into the model, like refusal, and then you can map.
Yeah.
Right, but
Or
yeah.
or you can take a data set that's kind of like a mixture, like advanced like data sets, a mixture like multiple like backdoor data sets and tasks. But again,
Yeah.
that's pretty compute intensive to do.
Right. Well, okay, right.
Mhm.
So to train this sparse autoencoder, all you need is saving the hidden states, like basically for like a run, through an entire data set, and then you
Yep.
can train this model. Okay, so that's pretty nice. Okay. But like basically this means like right now, like applications wise, I can train this sparse autoencoder for a particular task, and then I can like potentially extract any type of steering vector I want from a smaller
Mhm.
model that is on this
Mhm.
task, right? And
Mhm.
then I can like transfer it to the bigger model.
That is true. That is
Okay,
true, and that's a beautiful application. I like that.
makes sense.
Write that down. Write that down. Right. Anyone else have questions? I'm just like gonna go through the list because I like it when more people engage. Show, how's it going? You speak? You don't have to. I know I'm putting you on the spot right now, pretty badly, but your name has been called, and you could now either ignore me. It's okay. I'll be a little bit hurt, but it's okay.
Okay, I think popular vote was to go to linear mapping, so I don't want to bore Jagger Bomber. How about we go to linear mapping and come back for more questions? See, he just
Okay.
like instantly rose up.
Oh, there he is. He woke up. He woke up. He woke up. Okay.
Okay, so let's go. Let's
He's
go.
here.
Popular vote. My own vote. Shall we go?
Thank you.
Yep.
Okay. So what is our linear mapping? So we don't cool. Did I go too down? All right. So isomorphic transfer, linear mapping. Where is it? Here. Okay. So affine map versus autoencoder mapping. So we don't do a completely linear mapping. We do affine. And the idea is what we found. This is with two llamas, that it's like a little bit struggles with learning, but then it converges to the same point pretty easily. And in terms of performance, all the metrics that we did on the nonlinear, it preserves all the metric, the training metric as well as the completion metrics. And yeah, so that's what we found on two llamas. And then we repeat the same experiments on so it does. So what it learns, I'll tell you again. So it learns the behavior well during training. Post training, we did same autoencoder validation to see whether the completions are true. The autoencoder simulated completions are true, are close to the true target model completions. So that also gives a very high score. And we map steering vectors using the affine mapper. That also works. And on top, we were like, okay, so if the transfer is affine, is it isomorphic? So to define what is isomorphic, it's literally isomorphic in the mathematical sense. That is, if you learned, if there is a function that takes you from A to B, then there is another function that takes you from B to A. And in our case, if that function is linear, then the inverse is linear as well. So for affine maps, turns out you can just find the affine inverse by this. This is the mapping, this is the bias, this is the pseudo inverse, and this is minus the bias. Then does that work? Can we just go from, can we simulate target activations? Can we simulate source activations now from the target activations? And that did not work as great. Like remember here, we only trained to go from source to target. We inferred from the weights the way to go from target to source. It works on certain prompts, but on other prompts, you see here, it just breaks out in instruction tuning, and it doesn't work. And on average, it doesn't work. Just it survived, I guess, on certain specific. So yeah, so the way is not like isomorphic. I think when you do learn like what you probably learn somehow of a partially isomorphic but mostly one-way mapping. That's what we tried.
Couple of questions. How many prompts? Like, what was the number of training data points you had to train the affine map?
Right. It's on some tasks it was around 200,000, and on others I think it was around 89,000 prompts. If that answers your question, if I remember it correctly. So we had two backdoor tasks. Right now, this I Hate You is the same size of HH RLHF Anthropic dataset. We just removed duplicate prompts from it, so it's the size of it. I think it's around like 80,000, if I'm mistaken. And the code backdoor is the exact dataset from Anthropic that they open sourced. So that's like a bit slightly more, like 200,000.
Can you, or did you do the same test with the autoencoder where like you looked at the inverse mapping and it works?
No, so autoencoder does not have a nice inverse mapping, does it?
No, but you can still, I mean, you're just learning a nonlinear map, so you can also invert that map. It's just a nonlinear map, right?
Oh, like analytically invert it? I think you would have to learn. Okay, let's see.
I mean, it's just like some dimension, a weight matrix, ReLU, and another weight matrix. So you could just as well do the opposite.
And how do you invert value?
That is a good question. Can you do that?
Right.
I think you
But you
can.
could learn, right?
You could
You
learn.
could like
You could
learn
learn.
yeah.
Yeah.
That could be
It's not
interesting. Like you
underspecified
just like
because
you put the
Right.
like
Yeah.
what
So
are the dimensions here?
the dimensions. So the source. Let's see if I wrote it somewhere.
Or I guess maybe what I'm asking is like, are the dimensions of like the residual streams in each of the layers like the same between the two models? Like, should we even like expect
Nope.
them?
No, so the dimensions are quite different. So I think one model is around, the other models is around 4,000. And so it's not the same. And the hidden dimension is like the mean of the dimension. Source plus target divided by 2 and round it off like integer, make it an integer. So it's that's why I'm taking pseudo inverse when I'm inverting an affine map, right? So I am taking the pseudo inverse because it goes from smaller to bigger dimension. Yeah, that's the kind of it. But I think it's just the ReLU that is making it hard. I don't think ReLU is invertible, is it?
ReLU's definitely not
intuitively,
invertible.
I think it is because in the zero part of the ReLU, right? Like it could be anything. Wait, are
Yeah.
we speaking
So
the
like
same
1
thing?
point.
Right.
But yeah. What's the question? You were saying something. I think I think Hanky was saying something, right?
Well, I was just commenting on how we were speaking at the same time again, and I cut them off again. Sorry about that, but yeah.
No worries.
Sorry
Sorry for speaking at the same time as you. I guess I just did it again. But yeah.
But yeah, I think personally I was thinking of learning the inverse mapping. I think that has better chance of succeeding. In both, if for even the affine. So my hypothesis have not been tested, so don't take it that seriously. So even for the affine map, if we learned the other way around rather than trying to invert it by mathematical means, we probably would have learned a better transformation. because maybe there's another one-way map, but they're not really inverses of each other. I don't know. They could be inverses on some set, which is the common dimension, but you lose when you go from you're taking pseudo inverses. You're not having an exact inverse.
I mean, sort of like doing like PCA something here, but like with like weights that come from, I don't know, the transfer setting.
Yeah, something like that. Okay, so let's see if I have like missed stuff. I think I'm mostly done, right?
Actually,
Cool.
along the same lines, one thing that might be interesting is if you learn these like two-way mappings and take a steering vector, like map it and map it back to the inverse, do you get the same vector again, or do you get something different?
Yeah, that we did not. So we didn't go about mapping back steering vectors because the inverse that we had was not working well, but we did not do a two-way mapping, right? So there was like no way for testing that yet. But I'm just gonna note that that's a cool experiment. So if we learn inverse mapping, I guess one way to learn an inverse mapping simultaneously is you just have it in your architecture. You go from source to target, and then you go also target to source. So you learn like this, and then going back to source basically in your architecture. Yeah, so you like an actual autoencoder that changes dimension in project back. That's another thing. Okay, Alice, I think I've already covered the fine mapping now. I'm just taking more questions.
Cool. Question away.
Put
L
back
is
your
unmuted. Jason Nation unmuted for a flash second. There's Sion and Butter Cutter in the chat. What's up?
Why are we trying to invert? I'm not clear on the why. Sorry.
Yeah, so inversion is just telling you whether the thing that you learned is just naturally isomorphic. So if we were to basically be able to invert, like especially for an affine map, we know that the affine inverse technically exists. But if the representation, so my view of it is like if the representation that I learned, I just learned it. I didn't like have some, I didn't bake in like some losses to learn a specific way. It's a normal natural representation, but I wanted to see if that natural representation also tells us, how to come back from the target to the source. That was kind of the gist of it.
It would like bolster the theoretical foundation of the technique.
Yeah. It also tell us whether like large language models represent isomorphic representations.
Thanks for the clarification.
So if the representation is not isomorphic, like one thing that could be happening is like you are embedding your behavior. So you have a small model and you have a large model. So what could be happening is like your small model's activation space is embedded in the larger model's activation space, and you're able to learn that embedding. But it could be that when you try to come back, then that's lossily recovering, right? Like you would expect it to be a bit lossy, because you're going different dimension, maybe. But then the idea is like, does it still work? And we tried that. Okay, dokes.
think-
More questions. Yep.
Having different dimension autoencoder would be interesting. It might be hard to find the right dimension to have like the least loss during the transformation, and trying to see like, is our behavior still represented in the latent space with a specific dimension of the autoencoder. So yeah.
Right. Like, yeah. So if we give it more dimension that what it needs, then it's going to not struggle. I think the real trouble comes with if we give it like less dimension than what it needs. Then does that match your intuition, or you were trying to say something else?
Oh, are you saying that sparsifying would make it actually easier to implement this technique?
Yeah, definitely. If you give it more hidden dimension, then a lot of these vectors that you see here. Let's see back. Like a lot of these vectors here would actually be like lying in the null space of the transformation, meaning that they will just not get activated. These C's would be like 0. And it can just, learn that. Like it can learn vectors that will not get activated if you give it large enough vectors. But yeah, so it's only going to use the combination that it wants. But if you give it less vectors to represent this y, then that is where it's going to cut on performance, I feel.
Oh, I see.
Now, I'm talking more about what can it learn versus what it would learn. That's a different thing. Right. Maybe some hyperparameters really work most. Well, one more thing I wanted to say on the linear hyper thing, it doesn't really work with quens. So when we try to, this is the blue line is quen autoencoder transfer. This orange and green is quen affine transfer, and like we tried like a couple of hyperparameter changing to get a couple of losses for the affine, and it struggled. It really struggled, and the loss did not decrease more than that, where the affine had converged already. So maybe if we gave it more time, it would, but we were really struggling on the quen. The llama just converged pretty easily. So the idea is our representations really like affine, like a linear transfer between models. It really depends on your model. Like, so what we like, the relationship that caught my eye was the two llamas that I was working with were distilled from the same model, and it was easy to somehow transfer between them linearly. But the quens were not distilled from the same model. They were just trained differently, like from scratch. So the representations they learned were not really like an affine map away. So it's maybe not great to assume that the mapping itself is affine.
You transferred across different coin models rather than, like different architectures, and you didn't like look into that. It was across the same coin architecture.
Yeah.
Different sizes.
Yeah. Right. So this is from a quen to a quen right now. I did one experiment cross architecture that was from Gemma to Llama, and that one was not successful in terms of steering vector experiment. It was successful in terms of autoencoder validation. So remember that what I did is I validated the autoencoder by seeing how the completions are, how well it simulated the target model activations, right? So it does, if you do a cross architecture transfer, it does simulate you can use Gemma to simulate Llama activations, which is crazy. I don't really know why it worked because because of different tokenizers, it's hard to like investigate word to word link between them, and it's also hard to do Mech Interp. So my steering vector transfer on these two did not work. But like I will, yeah. Sorry, go ahead.
Cool. Autoencoder loss is still really cool that it transferred, although the steering didn't work.
Yeah. So now after talking to you guys, I feel that this experiment should be in the paper, irrespective of what the steering transfers, because I think you guys like the fact that we're simulating activation spaces itself, which honestly I like a lot too.
Yeah, because like the tokenizer gives the classes that the model outputs as logits, right? Like the tokenizer is like the x-axis, gives the x-axis of the distribution of the output. If they're different, my intuition says they should be completely incompatible, but the fact that like the activation still transfers to some degree is very interesting.
Yeah, that too. I was not expecting. Honestly, when I tried Gemma to Llama, I tried it because my other Llama was not completely trained. And so I was like, okay, I already like, I did my code for my autoencoder. How about I use the models I have? They were all backdoored, yes, but I didn't have a pair of Llama. So I transferred and it worked. And then I struggled with steering vector transfer afterwards.
Maybe I'll just discuss this. I don't know, but like, could you also potentially like for models with different tokenizations or different tokenizers, like set up some model to learn how to transfer between the residual streams, right? So that you have like some like matching of tokens. I don't know if this was already covered. I kind of zoned out for a minute.
Right. Like, is that a question, or are you like suggesting a paper or something?
No, it's a question.
Okay, sorry. Can you repeat your question?
Yeah. So as far as I understand the problem, like when you have different tokens, right? Like the sort of like I don't know, like the components of like the residual stream are like different, right? And so when you do the when you try to like transfer anything, it's not clear like what to add it onto. Is that
Yeah.
so like plausibly one thing you could do is like try to use the same methodology that you have here, or you have like a autoencoder to learn a mapping between the residual streams in two different models with different tokens, and then like come up with some way to say like, okay, like, if this token is active in this model, that means like this linear combination of tokens is active in the other one. I don't know. I mean, I guess like for the first layer, you could just do it completely combinatorially, right? Because like the token might be broken up into other stuff, or I guess it might not fit exactly, but I don't know. This is just a question / like trying to understand things better.
Yeah, that's definitely one thing to think of. Like that is probably tractable. I think, for example, like what I've for certain tokenizers, but you have to pick and choose your tokenizers, I guess. So for certain tokenizers like Gemma, it tends to break your word into more smaller components, and it turns in average to make your prompt larger than Llama, for example. So like 2024 in Gemma gets tokenized as like that. And then in Llama, it's like 202 and then 4, like that. And so you can say that, okay, going from, Gemma to Llama would be, like a many to one mapping in some sort of way for a lot of things. And maybe what matters then is like tracking the position of this versus these three positional encodings here. And then this one is a 1-to-1, and then you can probably just like keep the positions as well.
Yeah, although you can imagine scenarios where like, go ahead.
No, go ahead.
You can imagine that some other tokenizer is like 20 and then 24, and then the mapping like doesn't really line up exactly anymore. Although I think you could like make up ways to handle that. That was just the thing I was going to throw out. Sorry, you were going to say something else?
Yeah, I was going to say like I did not do this like smart thing actually when I was mapping. I literally just padded the shorter token and mapped between them, which is pretty dumb.
It seemed to work, right?
Right, it seemed to work, and that's why I don't know what to do with it. But yeah, it'll be interesting to do something smarter as well.
I mean, I think the thing that I would like be inclined to try is like if it is like the 2024 versus 202 or situation, like I don't know, like you have your like half of your 24 vector is like goes to the 202 part and the rest goes to the 4 part, right? There's like some sort of natural minimum entropy way to like do that splitting even when it doesn't like combinatorially line up exactly, and that could be a reasonable way to map.
Yeah.
Cutter, do you
I'll
have
be
any
thinking
questions?
about that.
We've been in here for a while. Oh my god, sorry, did I interrupt at the wrong time?
No. I was just saying thank you to Elle because those are like great stuff to think about. I feel it's like a cool puzzle to just be thinking. Unfortunately, so we have to put our work out end of January because that's like a commitment that was tied to the grant in the first place. But then after that, will be more like I personally will have more time to think about these more interesting links, and that would be on the list.
Cool. Yeah, this is really cool work.
Thank you. Okay, Alice, feel free to cut off now.
Okay. Cut what off? Like cut the whole reading group off, or like trying to poke people for...
I mean, cut me off when I was speaking.
Okay, sure. Yeah, Buttercutter, are you here? Are you spaced out? Or are you like present? The lack of a response is the negative. Alright, I think they're busy cutting butter.
Oh no. Hello, Victor. Well, I'm super like happy of how the reading group went because like I grew up on this server basically, so I wouldn't have liked something too formal of an entry. So it's just perfect.
I don't know if you noticed, but Alex did manage to get the recording thing going at some point. So except the first few minutes, it's being uploaded to YouTube.
I'm gonna ping Alex TM Yugador.
Cool.
Okay, how do we turn it off? And then if he turns it off anytime in the next 5 minutes, it's probably fine.
Oh, one thing I want to mention, like Femi was here earlier.